First of all, what's important to realize is that mathematics is very much behind. Most of these results are engineering results, very impressive, very spectacular, but we don't really understand the underlying mathematics. Now, why is that so important to understand the math? First of all, for efficiency. I mean, these algorithms take a lot of energy to optimize, requires a lot of data. Understanding of math is about potentially improving these algorithms, therefore having more efficient computations and more efficient in terms of data.
If we compare the steam engine in the 18th century to the AI revolution today, back also the trains were running, the companies were running, but we were not really understanding the scientific principles behind how the piston and vapor produce work. And it's only essentially half a century later that with Carnot and his work, we found what are the boundaries of the efficiency, what's the best possible efficiency that we can reach, and there is no point trying to do better. And when we do the analogy with AI today, it uses a lot of data, a lot of electricity to train it. And you could think that one cannot do better, but we don't know actually. Scientifically, we have not the understanding of whether we can do better or whether the way we are doing it currently is the best. So this is obviously important, because if we can do better, this would save a lot of resources and the understanding would lead to that. So to me, the analogy is very close.
Also, in terms of interpretability, these algorithms, for example, when you apply them to physics to predict the weather, somewhere they are able to understand the underlying structure of the physics. What kind of information do they extract? How can we understand that mathematically? It's important to then interpret the nature of the physics that has been learned. So there are a very wide range of important applications behind understanding math.
Yeah, so I think it's, as you say, it's a very special time where AI now has completely transformed into a very small discipline in the corner of computer science. Now it's really a central part of society. There's a lot to be gained by trying to integrate it further into the mathematical community, and some of the questions become mainstream mathematical disciplines. If we look at the past, there's many occasions where math has become richer and more interesting because it has interacted with things that matter in society and in the physical. For example, physics brought PDEs. We had also problems in engineering that brought harmonic analysis. And I think that AI is definitely ready to bring new problems, new interesting mathematical questions that we need to study.
Well, my career has most often been motivated by applied problems, but I think one has to realize that in history of math, most branches of mathematics have been evolving from applied problems. Even if you think 4,000 years ago, the appearance of geometry from the Egyptians, that was for measuring the surface of the fields, or the commerce for algebra. So, and if you move on, 17th, 18th century, physics was at the origin of very large branches of mathematics. So there is nothing new about the fact that mathematics evolves out of applications and problems that are raised by applications. As far as I'm concerned, what I like the most is to be in between, being on this bridge, going from the applications, but trying to understand the essence of the math which are behind.
Yeah, so there are different ways to answer that. One of them is not so much about the questions, but about the tools. That in order to understand what is happening in these neural networks that have many parameters, and the algorithm is walking, in a sense, in a space of all possible values of these algorithms and finding good values. It's a very high-dimensional problem. And it happens that it's physics that was historically the first discipline that started looking at these high-dimensional problems when it developed statistical physics at the beginning of the 20th century. So it's just a bit ahead in terms of looking at these high-dimensional probability distributions. So that's more on the methodological side. And on the kind of strategic side of how one chooses the questions, I would say that computer science, when it was developed, had a very small gap between mathematically rigorous proofs of the theoretical principles and the practice, the applications. But in physics, this was never true. There always was a big gap between the mathematics of proving things and the nature doing things, and physicists trying to understand the whole range in between. And that kind of in between, which is not the mathematical physics, but also the theoretical physics, the experimental physics, and only then the practice, the applied physics. Like, there is a lot of research space in between. And that, in my opinion, is something towards what computer science is developing, that the gap between the mathematics and the practice.
If you think of deep neural networks, what essentially they are doing is learning probability distributions. Now, you cannot learn probability distribution when you have a very large number of parameters, because the set of possible is exploding, which is called also the curse of dimensionality. How do neural networks learn these probabilities means understanding how they are factorized, what kind of structure they extract. This is essentially not understood. It's a very fundamental question, because this is about understanding the structure in physical problems, structure in biology. In general, it's about understanding how you extract structures to define knowledge, even from a philosophical point of view.
I think it's fair to say that dynamics is really at the heart of machine learning. We see it appearing in many, many different areas, moments. For example, training neural networks involves some dynamical process of gradient descent. Then we also see dynamics as the features of the neural network progress across layers. We now also see dynamics when we do generative modeling with all these diffusion models and flow matching, etc. And also it's clear that the randomness is a very, very central tool to understand many of the properties of these models. And so natural point of contact with the expertise also that we have here in Barcelona, it's very natural that then we took this opportunity to bring together the community of people working on PDEs, also in dynamical systems and beyond probability. And obviously these are just the examples of points of contact. What we hope is that maybe in the future we can also bring other areas of mathematics together.
To me, at the end of the day, what it brings is the kind of ultimate freedom, in the sense that as a species, as a social species, we kind of tend to be influenced by the biases of our community, of our group. If everybody around us buys an iPhone, we want to buy an iPhone. This is how we live. And this also pertains to research. When there is a research community, then the way we are asking the questions, the way we are approaching them, the way what we agree is important and what is not important is very much influenced by the others. And sometimes we are not seeing the full picture. Whereas when we go and see how different communities are asking the same questions, they do it very differently. So that forces us to rethink all those biases and, in a sense, free ourselves from them and really go towards the core of the scientific questioning without the biases created by the community or by the peers around us. So to me, that's a very valuable aspect of talking to different disciplines and seeing what is obvious and implicit and explicit for different disciplines.
I think it's very, it was an experiment, like a first attempt to try to bring AI into the conversation, to try to make it something beyond just a curiosity or something that you consume, and try to hoping that with this kind of workshops and bringing expertise from people working in other places, we can try to show the mathematical community here that there's interesting questions, and they definitely have a role to play in trying to push this field forward.